Hey, today we're looking at antiderivatives and indefinite integration. This corresponds to section 5.1 in our textbook. So the indefinite integration, now we're going to deal with definite integration later. Indefinite integration we're going to look at first. And this just means when you do it indefinitely that there are no lower or upper bounds. So you're not looking at a specific area under the curve, you're looking at the entire function. What is the antiderivative? So the opposite of the derivative of that function. What this means with the indefinite integral, when you evaluate it, you're going to have to add in a constant of integration. So plus c. Because remember, whenever you take the derivative of something, any numbers added or subtracted after just go away. So when you go the other way and do the antiderivative, you have to add in the plus c because there could have been a number there that got erased. So you have to kind of add in that little trail of breadcrumbs for yourself to say, well, there could have been a number here. We don't know what it is right now, but we want that placeholder there. So generally, the antiderivative be a capital Fx. So remember, I talked about the ladder, and then what rung are you on the ladder? So when you're taking the derivative, you have f of x. Take a derivative, move one rung down at the ladder, f prime x. So velocity. Take another derivative, you're one rung further down, so f double prime of x. Well, so far in the first semester, we only moved down the ladder. Well, now with antiderivatives, we can move up the ladder. So you can go from f double prime to f prime, from f prime to f. From f, you can go up to big F of x. Now, we won't see that notation very much, but if you do, now you know, okay? So if you have f of x equals 3x squared, so we're right here, okay? And you want to take an antiderivative, you got to think to yourself, well, what was the original function whose derivative was 3x squared? Well, to get 3x squared, you'd have to take the derivative of x cubed. But any number would be eliminated to go away. So was the x cubed plus 1, x cubed minus 7. So without any additional information, without any what we call initial conditions, we say plus c. There could be some number there. That number could be 0, but it also could not be. So we kind of leave ourselves some wiggle room. If there's a number, it can go in there for C. Some basic integration rules. These look a lot like limit rules, derivative rules. But number 6 is the one I want to focus on. Remember we started derivative rules by doing the power rule for derivatives, bring the exponent down, decrease the exponent by 1. Well, this right here is the power rule for integration. So kind of like inverse operations, you gotta undo everything that was done in the power rule for derivatives. So the n exponent that's going to get increased by 1. So when you do derivatives, you decrease. Now you get an increase. We're then going to divide by the new exponent. Remember, derivatives, you'd bring the exponent down, decrease by 1. Well, now we're going to increase the exponent. We're going to divide by that new exponent. So 3x squared. Sorry, the indefinite integral of 3x dx 3x squared. What am I thinking? So increase your exponent by 1. So x to the second. And then divide your coefficient by your new exponent. So your coefficient 3 divided by your new exponent 2. And don't forget, plus c. And if you want, check your work. Take the derivative of 3 halves x squared. Derivative of 3 halves x squared. Bring the exponent down. 3 halves times 2 is 3. Decrease the exponent by 1. So to the first, the plus c and the numbers get rid of it. And you have what you started with. So we're starting small, just like with the derivatives. We're starting basic, okay? 1 over x cubed. Not a bad idea to do a rewrite. And then go ahead and do your power rule for integration. Increase the exponent by 1. And be careful, -3 increased by 1. So x to the -2. And then divide by your new exponent. So we have a 1 coefficient, so 1 over -2. And don't forget to plus c. And you simplify that down, 1 over -2 x squared. Kind of doing that, oh, that's a bad line. Kind of doing that algebraic manipulation if you have to. Example C, not a bad idea to do a rewrite. So the indefinite integral of x to the 1/2 dx. So go ahead, evaluate. Increase your exponent by 1, so 1/2. Increase by 1, x to the 3/2, and divide your coefficient by your new exponent, so 1 over 3/2 plus c. So 1 divided by 3/2, you don't divide by fractions, you multiply by the reciprocal. So 2/3 x to the 3/2 plus c. And if you wanted to rewrite it, 2/3. I'm sorry, oh, gotta get those 3/2, so square root x cubed plus c. There you go. Example D. Again, not a bad idea to do a rewrite. So let's take that cube root, make it x to the 1/3, quantity x minus 4 dx, and then distribute your x to the 1/3 in. So x to the 1/3 times x to the 3/3, x to the 4/3 minus 4x to the 1/3 dx. Now it gets a little sloppier with the fractions, but just go through the same process. X to the 4/3 increase it by 1, so 4/3 becomes 7/3. divide by your new exponent, so divide by 7/3, that's 3/7, minus x to the 1/3, now increase by 1, so 1/3 plus 3/3 be 4/3, and then divide by the new exponent, so 4 divided by 4/3, or 4 times 3/4. And don't forget constant of integration, plus c. Example E, same thing, wherever you're at. It looks kind of sloppy. Clean it up. So x plus 1, x to the negative 1/2 dx. Then distribute the negative 1/2 at the x to the negative 1/2 in. So indefinite integral of x to the 1/2 plus x to the negative 1/2. Then go ahead and do your power rule for integration. So x increase 1/2 by 1, so now 3/2. Divide by your new exponent, so 2/3. And negative 1/2 plus 1, that is 1/2. Divide by 1/2, so 2. And plus c. So kind of like with the derivatives at first, took a little bit to get used to it, but then just keep practicing, and practice makes better. So t squared plus 1 squared, to do yourself a favor, expand it out. So t to the 4th plus 2t squared plus 1. And then our independent variable is t, so dt. And then t to the 4th, increase exponent by 1, so now t to the 5th, divide by 5, so 1/5, plus t, now t to the 3rd, divide by new exponent, 2/3, 1 becomes t, and don't forget, plus c. So just going backwards from what you saw at first with the derivatives. A good old trig function, so kind of some of these are the reverse of what you're seeing. So the integral of cosine, kind of think what would you take the derivative of to get cosine? Be sine of x plus c. Integral of sine of x dx, so what would you take the derivative of to get sine x? That'd be negative cosine x plus c. And then the others you gotta kind of memorize. So cosecant squared is negative cotangent x plus c. Secant squared is tangent x plus c. Maybe you remember derivative of tangent is secant squared, so now reverse it. Indefinite integral of cosecant cotangent x. Going to be negative cosecant x plus c. And for secant tangent, that would be secant x plus c. Alright. Had the thought, but it ran away. If I remember, I'll tell you. If I don't, it's not important. Or it is, and I forgot. Sorry. Okay, so indefinite integral of 2 sine x dx. So the integral of sine is negative cosine. So the 2 coefficient goes along for the ride. We have negative cosine of x plus c. There we go. Sine x over cosine squared. You could rewrite this, break it up to 1 over cosine x times sine x over cosine x. 1 over cosine is secant of x. Sine over cosine is tangent x. And secant tangent, why do I write plus c? I want dx. There we go. And secant tangent is secant of x plus c. Now the plus c is if you don't know what the number would have been, if you don't have any initial conditions. So let's look at an example where there are some initial conditions. Right here and here. We know that f prime of 2 is 5. And know that f of 2 is 10. So we know some points on the derivative in the original. We can use those to kind of fill in the gaps from this indefinite integration. So f double prime of x is 3. So let's go one rung up the ladder. Go to f prime of x. That would be 3x plus c, because the derivative of 3x is 3, derivative of c, which is a number, would be 0. But now we have this initial condition. F prime of 2 is 5. So 5 equals 3 times 2 plus c. Plug in 2 for x, and then 5 is for your f prime of 2. And you solve that. And since we're going to a first derivative and then again to a regular function, we'll have multiple constants of integration. So let's call this c sub 1. So c sub 1 is negative 1. So to plug that back in, f prime x is going to be 3x minus 1. So we found a specific f prime function. So now let's do that again. Go to f(x). So, and in the antiderivative of 3x, x increased exponent by 1, x squared, divide coefficient by new exponent, so 3 halves. Minus 1 would be minus x, and then our second constant of integration. So now let's plug in our second initial condition. F of 2 is 10. So f of 2 is 10. And plug 2 in for all the x values. And we'll solve for c sub 2. So 10 equals, so I see 3 halves times 4, be 6. Minus 2 plus c sub 2. And you end up with c sub 2 equals 6. So our specific or particular solution for f of x is 3 halves x squared minus x plus 6. And if you want to check your work, go ahead and take 2 derivatives of your answer, and you should get your f double prime. So take a look at example 5 and check your work with my completed notes online.